All right, so now we're going to discuss explicit symplectic partition Runge-Kutta methods and see how they can be viewed as variational integrators. Okay. So the first observation, if you will, is that Hairer showed that all explicit symplectic partition Runge-Kutta methods can arise as the composition of some underlying sort of one-step method. Okay, so let me sort of show you what that is. It's like, and then we'll talk about how then you can interpret that as a variational integrator. So Hairer. So this is Ernst Hairer showed that all explicit symplectic partitioned Runge-Kutta methods can be obtained as the composition of sort of an underlying one-step method which I'll denote FAB. Okay, so FAB is a map from T star Q across the rails to T star Q. So the real part again is the time step, and the method looks like the following: Q 1 equals to Q0 plus AH M inverse P0. And if you think about it, if you have a simple mechanical system, then M inverse P0 is really just the initial velocity. Okay, and then P1 is equal to P0 minus BH, the gradient of the potential at Q1. Okay, so all explicit symplectic partition Runge-Kutta methods can be obtained by composing this method for suitable choices of A and B, and its adjoint. Okay, and their adjoints. Okay, so what we're going to show basically then is that this underlying method can rise from a discrete Lagrangian, which then generates a variational integrator. Okay, so the claim is that this FAB map, right, is equal to the Lagrangian, so the discrete Lagrangian flow map. So that's denoted by F tilde, right, for a discrete Lagrangian, right, where the discrete, and let's just call that LDAB, where the discrete Lagrangian is given by the following. So LDAB Q0 Q1 H, right, it's going to be H times B 1/2. So this is going to be something like a finite difference approximation of, it's like the Q dot M Q dot term, right? So this is Q1 minus Q0 over H, which is like a Q dot approximation, M Q dot, right? So this is sort of a very reasonable approximation of the kinetic energy piece, okay? And then minus 1 over A V at Q1. Okay. All right. So we say that this is the. All right. So the claim then is that if you were to take the Hamiltonian flow map, discrete Hamiltonian flow map associated with this particular discrete Lagrangian for these parameters A, B, then this gives you this map, okay? And then we know that if you have one of these discrete Lagrangians, you can get the adjoint of that, right? So there's the adjoint discrete Lagrangian. If you recall, let's see. Right, so the adjoint discrete. So then there's the adjoint LDAB star, right? Q0, Q1, H, right, is equal to minus LDAB, where you swap the order of the parameters and you change the time step to a minus, right, H. All right, so, and then, all right, so the adjoint of this method, right, is equal to the Hamiltonian flow map of the adjoint discrete Lagrangian, right? Okay, so what that again tells you is that both this method and its adjoints can be obtained by some suitable choice of discrete Lagrangian. And then finally, it's like what you want to do is you want to be able to take compositions of this. And we discussed sort of earlier when we talk about compositions of variational integrators that there's a way to think of the composition of the variational integrator as arising from the discrete Hamiltonian map of some composition discrete Lagrangian. And so again, it's like the composition falls into this category of variational integrators. So what that basically tells you then is that because the fact that all explicit symplectic partition Runge-Kutta methods can be obtained by the composition of this method and its adjoints, and the fact that this method and its adjoints can be viewed as discrete sort of Hamiltonian maps associated with discrete Lagrangians, and since the composition of discrete Hamiltonian flow maps can be expressed as the Hamiltonian flow map of a composition discrete Lagrangian, that means that all explicit symplectic partition Runge-Kutta methods can be expressed in terms of computable discrete Lagrangians. Okay, so let me just stop there for now.